Okay, so I think I will get started. So yeah, so in today's class, I want to talk about like this section 5.4. So I think it's I read like your research projects, and I realized that most of you want to do some like the effect of X on Y. Okay, so it's you want to study like those correlation effects. Okay, so so for example, I know some of you want to study like the effect of like the COVID on unemployment rates, the effect of COVID on gasoline price. Yeah, so you want to do this, and we do not cover a lot of like that in previous classes, but like to include like those X variables. So for example, like to include like the COVID into the regression model is not that hard, but it requires some work. So in today's class and maybe next class, I want to talk about this. Okay, so basically like how we can generalize our previous SREMA model to by including some regressors. Okay, so let's talk about it. Okay, so in economics, we want to study the effect of X on Y. So let's first start with like the cross-sectional data or the panel data as a motivation. Okay, so that's the model we have. So yi equal to xi beta plus wi. So wi is the error term, xi is your regressor, and yi is your response. Yeah, and we know that if xi is independent with wi, then use OLS to find beta. Okay, so that's very standard results. So if xi and wi are independent, then we can use OLS to find beta. However, in most economics application, xi is not independent with wi. Okay, that's like really standard thing. Okay, so for example, like if you want to study the effect of the education on wage, so that's the perhaps the most famous example. So if you want to study the effect of education on wage, and what could be the error term? The error term could be your ability, because the ability could also affect your wage. And if that is the case, then we can easily see that the education level is not independent with the ability. It is actually related with the ability. Okay, so if this is the case, then we cannot use OLS to find beta. Okay, so if xi is not independent with wi, then we cannot use OLS. So OLS would not give us a unbiased, would give us a unbiased, inconsistent estimate of beta. So which is not something we want. Okay, so how can we address this problem? So in economics, there are a couple of ways to address this problem. Yeah, and let me tell you, this is sometimes called endogeneity problem. If it is independent, we call it the exogeneity problem. So if we have like this endogeneity problem, we have a couple of solutions. So one solution is to introduce some other random variables. So for example, we call it like the instrumental variables. So those instrumental variables are related with your X let me see, it's related with your X, but it's not related with WI. Okay, so you can use the instrumental variable technique to address this endogeneity issues. And I think the like this instrumental variable you have seen in your Econ 4631. Okay, and some other solutions include like the control functions. So you perhaps not seen that in your early class, but it's very closely related to the instrumental variable. And another solution is called the panel data solution. Okay, so that's a solution we will focus today. Is the panel data solution. So the panel solution, the panel data solution, the idea is that we will use like more than one period of data to address these endogeneity issues. Okay. So the setup of this panel data is like this. So let's assume like YIT is equal to XIT beta plus WIT. Okay. So now the data depends on I and T. Okay. So you'd say like the subscription is different. So originally we only have like one period of data, but now we say that we have more than one period of data. Okay. And assumption here that people make is so people usually assume that WIT consists of two components. One is a time invariant component, let's call it WI. And another component is epsilon IT, the time varying component. Okay, so this is the time invariant, and this is a time varying. So for example, again, back to the very famous education wage example. So if you assume that the error term includes the ability, then it is highly likely that the ability does not change across times. Okay, so that means WI is the ability, it does not change over time. And epsilon IT, you can think of it as some other random terms. Okay, that affects wage. People assume that WIT consists of two parts. One is a time invariant, and the second is a time varying part. Okay, and moreover, we assume WI is not independent with XIT, but epsilon IT is independent with XIT. Okay, so again, just as what I said, if you think WI is ability, it does not change over time, and it is actually definitely not independent with your education level. And you can also think that some epsilon IT has some random shock to your wage, and it is independent with your education level. Okay. So if we have these assumptions, if we have these two assumptions, one assumption is that WIT consists of a time invariant part and time varying part. And the second assumption is the time invariant part is not independent with the error term, and the time varying part is independent with the regressor. Then you can have this. Okay. Then we can have this. So let's suppose that we have YIT equal to XIT beta plus WI plus epsilon IT. Okay, and we can also have YIT plus 1, XIT plus 1, beta plus WI plus epsilon IT plus 1. Okay, so this is a very standard panel data setup. Okay, and in the panel data, people like to call this WI maybe the fixed effect. This is like the random effect, yeah, something like that. If you like took like some other econometrics class, like the instructors might introduce the things in that way. But now let's just have like forgot about those and just think like the error term consists of a time invariant part and time varying part. Okay, so if this is the case, then we can actually estimate beta without no problem. So how can we do that? We can take the first difference to kind of say the same idea. That's what we use in the series analysis. So this is just a first order difference. I just subtract the second equation from the first equation. Okay, so this is epsilon it plus 1, epsilon it. Okay. And now you can see this part is equal to 0. The Wi no longer exists in our model. Okay. And what we left is just yit minus yit plus 1 xit this is not correct, so this is epsilon it minus epsilon it plus 1. Okay. All right. So because epsilon it plus 1 are independent with xit and xit plus 1, this is our assumption, then you can regress yit on xit minus xit plus 1 to get beta. Okay, so we use this like the first order difference idea to get rid of the problem part, which is this Wi, this time varying part, this time invariant part. Okay, then we reduce it to a model that without this Wi. Okay, then we can run a regression to estimate this beta. Okay, so that's the idea of the panel data. The key part is that the first difference. The key part is the first difference. Okay, so let me go over this again with you. So the problem we have for this regression model is that this error term is not independent with the regressor. Okay, so if this is the case, then we cannot run a OLS regression to find beta. Okay, and this is a problem people usually call it like the endogeneity problem. And to address this problem, we assume that we can observe 2 periods of data, or at least 2 periods of data. And we assume that the error term consists of a time invariant part and a time varying part. Okay, and we further assume the time invariant part Wi is not independent with xit. However, the time varying part epsilon it is independent with xit. Okay, so if we make all these assumptions, then we can take the first difference to get rid of this problem part Wi. And then since there's no Wi exists in this model, we can run a regression to get beta. So that's the idea. Okay, so that's the idea of the panel data. And also the idea in the cross-sectional data, if we have some endogeneity issues. Okay, so now we can somehow use the same idea to address this like endogeneity problem in the time series data. Okay, so let's go back to our focus, the time series data. Okay, so the time series data looks like this. Okay, so let's say yt. Okay, so here instead of yi, we are like observe the data period by period. So it is yt. So let's say that yt is equal to let's change a name. Let's call it like zt beta plus let's call it xt. Okay, and this zt is your regressor, and this yt is your response. So for example, I know people study like the effect of COVID on some economic variable. And if that is the case, then this zt is the COVID, and this yt is your variable that you would like to study. Okay, and this xt is an error term. Okay, so in the time series data, if xt is stationary. So that's the difference between the time series and cross-sectional data. So in the cross-sectional data, we say that if xt is independent with like the regressors, if the error term is independent with the regressors, then we can use the OLS to estimate beta. And here, if xt, if the error term is stationary, then OLS works. However, if xt is not stationary, then OLS does not work. So if you run an OLS, but if your error term is not stationary, then you cannot consistently estimate beta. Okay, so that is a problem. Okay, so let's say suppose xt, say example, it's let's say it follows an ARP process, and it's not stationary, then you cannot run an OLS. Okay. So we need this xt to be like white noise in order to run this OLS regression. Okay, so if we have this problem, and this is like usually the problem, right? So for example, let's say that if you want to study like the effect of like the COVID on unemployment rate, okay? And let's suppose that you took away that COVID-19 effect, then do you think your unemployment rate is stationary? Okay, so if you took out like the, let me write, so I say if your YT is your unemployment, and the ZT is the COVID. Okay, and YT minus ZT beta is something left. Okay, is the unemployment without COVID. Okay, so do you think, and this is equal to your error term xt. Okay, so do you think if you took away the COVID effect, do you think like your unemployment is stationary? Highly likely it is not, right? Because even we took away the COVID effect on unemployment rate, it is very high. It is highly likely that the current period unemployment rate is related to previous period unemployment rate. So that would make YT minus ZT beta, which equal to XT, unstationary or not stationary. And if that is the case, then you cannot run an ORS to find beta, to find your parameter of interest. Okay. So how can we address this problem? Okay, so we will use the same idea as panel data to address it. Or to be more specific, we will try to get rid of the unstationary part of xt. So that's our idea. Okay, so we will try to make some transformations on the data in order to get rid of this unstationary part of xt. Okay, so once we make this xt stationary, then we can easily run an OLS. Okay, so this is exactly the same idea as in the panel data. So in the panel data, we take the first order difference to get rid of this problem part. Okay, and here we will also make some transformations on the data to make our error term stationary. Okay. So how can we do that? So let's start with some simple case. So if xt just follows a very simple ARP process, okay, then that means VB xt is equal to WT. Okay, and this WT is the white noise. Okay, and this is the backshifter. Right. Okay, so knowing that, how about we multiply phi b on both sides of our regression model? So phi b yt equal to phi b zt beta plus phi b xt. Okay, so we multiply phi b on both sides. Okay. Now how about we call this yt star? And let's call this part zt star beta plus wt. Okay, so now wt is white noise. It is stationary. That means we can run an OLS regression to get beta. Okay, so WT. Okay, so did you see that? So the same idea we use as the panel data. Okay, so we make some transformations on the data to take care of the problem part. Okay, so that's the XT is an ARP process. Similarly, you can imagine, let's say that if XT follows a ARMA process, ARMA PQ, then that means phi b xt is equal to theta b wt, right? And that further implies if you like move the theta b to the left-hand side, that is theta b negative phi b xt equal to wt. And let's call this part just pi b. And if this is the case, we can just multiply pi b on both sides of the equation. Okay. This is WT. Okay. So again, OLS works. Okay. So and we can even generalize, let's say that if xt follows an S-arrayma, we can do the same thing. We can do the same thing to make the error term stationary. So I won't write this down, but you can verify yourself. We can do the same thing as long as xt is a valid S-arrayma model. So if it is a valid S-arrayma model, we can always iterate as a AR infinity process, a valid AR infinity process, and then we can like do this multiplication on both sides to get rid of this unstationary part of the xt. Okay, so that looks pretty good and pretty straightforward, right? But the problem here is xt is not observed. So if xt is not observed, we can just easily fit an S-arrayma model to it. Okay, if we assume it follows an S-arrayma process, we can easily follow an S-arrayma process to it, and we can get those coefficients and use those coefficients, and we can multiply like both sides of the data by those coefficients, then rerun the regression to get the beta, right? So that's the idea. But the problem here is that the XIT is not observed. Because it is not observed, so that means we cannot fit a S-arrayma directly. right? The question is, how can we address this? The answer is we have to estimate xt first. So step one. So this is a very yeah, I will have like a more detailed step in the R code, which I will show you later. But now let me just write this like a simple step, okay, easy step. So step one is that we run OLS of YT on ZT and obtain residues. XT equal to YT minus ZT beta. Okay. Step two, fit a S-arima to XT. Okay. Step three, we run OLS of YT on ZT and the S-arima of XT to obtain beta. Okay, so that's the steps that we will use to estimate beta. The idea is that we will first estimate XT, then we will use that estimated ST to fit an S-arima model. And once we fit an S-arima model to it, then we will use basically we will use the coefficient of that S-arima model to like retransform. I mean to transform our data and to rerun a regression of the transformed YT on the transformed ZT to obtain beta. Okay, so that's the like the ideal steps. Okay, but there are a couple of like problems with these steps. Okay, so problem number one. So which ZT you will choose? Okay. So what's remember, yeah, so I will use like the homework question as an example. So in the homework question, I think we want to study the effect of the leads on the sales, right? So that if that is the case, the question asks you what legs of the lead you want to include in your model. Okay, so here is the same idea. Suppose that you have a bunch of ZT, then what ZT you want to choose? Okay, so we will cover this. So we will use like the cross correlation check. To pick ZT. And problem number two. What arima model or what S-arima model you want for XT? I say like in step two, we need to fit an S-arima model to XT. The reason is that we want to get rid of we want to make our XT stationary. Okay, then the question is, what S-arima model you want to use? And the answer is easy. We spent like pretty much all the previous classes talking about this, how to fit an S-arima model to a time series. Okay, so the solution to this is easy. Check previous class. Yeah, so I also have the detailed steps later in the R code. So we will do like all this, like the coefficient check, the residual plots check, the AIC, BIC check to find the best ARIMA model for XT. Okay, so problem 1 and problem 2 are not big deals. We know how to address those. And the problem that whiteboard that is actually a little bit hard is problem 3. The problem 3 is that run a OLS of YT on ZT in step 1 is not correct. We cannot get the correct ST. So let me go back. Okay. So you see that in step 1, we need to run an OLS of YT on ZT. Then we obtain the residuals. However, you should notice that we actually cannot run an OLS of YT on ZT, right? Because this XT is not stationary. So that means running an OLS of YT on ZT is basically not correct. It's not the correct thing we want to do, right? If we can run an OLS of YT on ZT, that means the XT, the error term, is stationary. Then there's no need to do all this like following steps. There's no need to do like this as ARIMA fits and to rerun the model. There's no need to do that if like running an OLS of YT on ZT is valid, okay? But I mean, people still do that, even though it is not like 100% correct, but people still do that. And there are some corrections for that, which we will not cover in this class. So basically you can like do this in an iterative way, then in order to get like the correct XT, okay? So so we will not cover those like techniques here, but those are just some corrections. It's not like 100% correct. So I mean, the easiest way people like to do is just to, as the first step, just assume that we can have a feasible estimator of beta, then do the rest of the stuff. Okay. Yeah, so that's problem 3. It is the thing that it's a little bit hard to find a solution. So in our class, and I think in most of the applications, we will just assume as the first step that we can run a OLS of YT on ZT to obtain the correct residuals XT. Okay. Okay. Yeah, similar question here. That's running when you aren't supposedly correct. Yes. So yes. So if like the XT is not stationary, then running an OLS of YT on ZT would not give you the correct beta and would not give you the correct residuals. Okay, so that's my point here. Yeah, but I mean, people still do that, and let's just follow that convention to do it. Okay, so any more questions? Okay, so if there's no more questions, I think I want to switch to R and give you a detailed example of doing this. Okay, so this is our example. So I already posted that on Moodle. So if you want to go with me, you can download it from Moodle, and I will post the updated version after today's class. Okay. Yeah. So so first let me talk about like the detailed steps of doing this regression. Okay. So that's I call it the steps to fit a S-Arima model of Y with a regressor X. Okay. So step one is that we use the CCF and the lag plot 2 to determine what lags of the regressor should be included in the model. Okay, so we will check like the cross correlations between Y and X and decide which lags of X we want to include in the model. So we will basically pick the lag of X that has the largest correlation with Y. Okay. And the second step is to regress Y on the chosen lags of X, and we obtain the residuals. Okay, that's what I just discussed. So we'll regress the Y on X and obtain the residuals. Okay, and we implicitly assume that is a correct regression, even though it is not. Okay, then step 3 is that we will fit a S-Arima model to the residuals by looking at the plot of the residue, the ACF, and the PACF plot. Okay, so that's exactly what we learned in previous class. Okay, we treat the residuals as a new time series. We plot its ACF, we plot its PACF, and we fit the best S-Arima model to it. Okay, yeah, and to fit the best Arima model, you need to check the like all those stuff to determine the best S-Arima model. Okay, then step 4 is that we regress Y on the chosen lags of X plus the chosen S-Arima of residuals. Okay, so this step is basically we transform Y and X to its correct form. And now if we transform that, then the residual is white noise. Then we can run the simple OS. Okay. And step 5, because like you run that regression, you need to check if this is like a good regression. I mean, if this is a good model. So you check the coefficient of significance, you check the residual plots, you check the AIC, BIC, and etc. of your regression model. Okay. And you need to consider many models. So for example, you need to use different lags of X. This is in step 1. Okay. You need to consider different S-Arima of residuals. This is your step 3. Okay. So to decide the best final model. Okay, so now just remember now the parameter of interest here is the beta, the XT beta, the coefficient of your XT, the coefficient of COVID on your economic variables. Okay, so that's our goal, and here you can actually like interpret beta. Okay, so for example, if like your question is the effect of like the COVID unemployment rate, and if you find like the beta is say like I don't know, like a negative 0.2, let's say 0.2, then that means for a 1 unit increase in the COVID-19, then the unemployment rate will increase by 0.2. Okay, then in this case, you can actually interpret beta as cross-sectional data. But in the time series, you cannot, it's not a good idea to interpret the beta. Okay, but here you can do that. And that actually makes things more interesting. Okay, so that's step 5. And step 6 is that's doing forecasting. But doing forecasting here needs to be very careful. So perhaps I do not have time talking about the forecasting in today's class, but I will definitely talk in next class. Okay, so some simple extensions. So what if we have more than one regressor X? Okay, so the difference is just step 1. So we just plot the cross correlation between Y and each X and find the potential lags of each regressor. Okay, so yeah. That's just very simple extension. Okay, so that's, I think, a pretty detailed steps of fitting a S-Arima model of Y with regressor X. Okay, so now I think I want to do this example with you. So this is the question that you already did in your homework. So it's question 5.13. But I think the answer is not that comprehensive. So I want to do it like in a more comprehensive way. Okay, so part A, so I won't do part A that much. So part A just says that fit an ARIMA model to ST. ST is a monthly sales data, and discuss your model fitting in a step-by-step fashion, presenting like all those stuff. Okay, so I think I won't do that, just very quickly go over it. So I just want to very quickly go over it. So I first plot the sales data, definitely a increasing trend. So we take the first order difference, looks not that bad, and do the ACF plot. So the ACF and the PACF plots are here. So from here, we can tell that the ACF like tails off and the PACF cuts off at either leg 1 or leg 2, right? So the model that we have in my mind perhaps is the S-ARIMA 110 or S-ARIMA maybe 111 or 211. Like that. You just try it, and I tried and I find like the best model is just ARIMA 111. Okay. Okay, so that's question A. And now let's move to the question that I really want to talk. It's question B and C. Okay, so question B and C, the question B says that use the CCF and the lag plots between the difference of sales and the difference of lead to argue that a regression of the difference of ST and the difference of lead -3 is reasonable. And part C says that you want to fit a regression model of the difference of the sales and the difference of the leads -3. Plus, that's it. And discuss your results. Okay, so that's part B and part C. So the part B, the textbook question basically just asks you to fit a regression model by using lead -3. However, I checked the plots. I feel like lead -2 might also be important. Okay, so let me do all this with you. Okay, so the first step is that I don't know why I do this, but I plot the ACF plot. Yeah, the first step is that that's the step 1 here, to use the CCF and the lag point plot 2 to determine what legs of regressors should be included in the model. Okay, so I do the CCF plot. Okay, and I find that it seems that the 1, 2, no, 0, 1, 2. So leg 2 and leg 3 are the largest correlations, have the largest correlations. And more importantly, both of them are outside of the confidence interval. Okay. And this leg 2 dot plot command gives us this detailed plot. Okay. So we can easily see that when it's least leg 2, the correlation is -0.38. And when it is lead leg 3, the correlation coefficient is 0.72. So both of them are significantly larger than other correlations. Okay, so that's what I write here. So it looks like that lead -3 and lead -2 have strong relations with sales. Okay, so we will use lead -3 and lead -2 as our potential regressors. Okay. So what I do here is that I first consider only including leg 3 in the regression model, and this is exactly what the textbook question says. Okay, so we only include leg -3 in the model, yeah, because leg -3 has the largest correlation. Okay, so now how to set up X and Y here? So how to set up the data? Okay, so let me write this I write something here. Okay, so let's suppose that sales only have 5 observations from 2000 to 2004. Because we will do the sales with lead -3, right? That means we will only use 2003 and 2004 data, okay, in order to match the lead data. because for the lead -3, we can only use 2000 and 2001, right? 2003 sales matches lead 2000, and sales 2004 matches lead 2001, right? Because we use lead -3. So that means we need to get rid of some of the data in order to do the correct match. And the data that we throw away for the sales is the first 3 observations, 2000, 2001, 2003. And for the lead data that we throw away is this last 3 observations, 2002, 2003, and 2004, okay? So using this same idea, let's go back to our data. So for the sales data, we throw away the first 3 data, 1, 2, 3. So this minus means that we get rid of like we throw away those data. Okay, so we throw away the first data point, second data point, and 3 data point of sales. Okay, exactly the same thing here. We throw away 2000, 2001, 2003. Okay, and similarly for the lead data, we throw the first 3 observations. Okay, so I check like we only have like 149 data, so we will throw 149, 148, and 147. Okay, so same thing here. We throw away 2004, 2003, and 2002 data. Okay, so this would make us the correct match between the sales and the leads. Okay, so any questions here? Okay, let's run these 2 codes. And now the new data, I call it DS3, so the difference sales 3 and difference lead 3. Okay. Then we will do, I think we will do our step number 2 to regress Y on the chosen leg of X and obtain residues. Okay, so here is that we do this simple linear regression model, DS3 over DL3. Okay, and let's plot the residues. So here's a residual plot. So you can see the residual plot is not bad, right? It's there's definitely no trend. I do not see seasonality pattern here, and I do not see much heteroscedasticity here. Okay, so yeah, so that's what I say. So the raw residual plot shows no trend, no seasonality trend. And if I run the ACF and the PCF plot of it, it confirms this, right? From the ACF plot, we can see it dies very quickly. And both the ACF and the PACF does not show any seasonality pattern. Okay, so the ACF plot confirms this. Okay, so then the step number 3 is to fit a S-ARIMA model on the residues by looking at its plot and its ACF and the PACF plot. Okay, so we look at this raw plot, looks good. I mean, not good, but definitely it's like there's no difference or no seasonal difference we want to do. And this ACF and this PACF plot suggest that we perhaps want to use ARIMA 100 as our starting point, right? Because this ACF dies like tails off, and this PACF cuts off at leg number 1. So they suggest that a ARMA10 model is a good model since we do not do the difference. So this is ARIMA 100 model. Okay. Yeah, and also since there's no seasonality, so we do not need to put add seasonal coefficient here. Okay, so then that's the step number 4 is to regress Y on the chosen legs of X and the chosen S-ARIMA of the residues. Okay, so that's what I do here. So this S-ARIMA on the time series DS3 and the X chosen X is DL3. Okay, and the S-ARIMA model for the residue is 100. Okay, so we run this code, and this is what we got. Okay, so the next thing that is you want to check all this stuff. So first checking the coefficients. Looks like all of them are statistically significant at 5% level. And I check the residual plot. Everything looks good. Okay, yeah, actually, yeah, everything looks very good. Okay, and the AIC, BIC here, the AIC is 2.366,
and the BIC is 2.448. Okay, yeah, so looks like our starting point is good. But how about we increase the order of our starting point a little bit, and let's see what happens. So what I do here is that is basically this command. Here is that I regress the DS3 on DL3, and the residual as a remnant of the residual I consider is 101. Okay, so it's ARMA 11 model. And this is the thing I got. So again, you can see the residual plots are good. Not that bad, but we can easily tell that the coefficients of this MA1 is statistically insignificant. Okay, and moreover, the AIC and the BIC here are both, I think, larger than the model we considered earlier. Okay, yeah, so that means this model is worse than the first model. Yeah, and I also consider this as the RIMA 2000 model. And it seems to me, same problem. So the coefficient of AR2 is statistically insignificant. The AIC and the BIC are both larger than the first model. Okay, so I write something here. So by checking coefficient significance, yeah, and also, by the way, since you can also check the, let me show you. So you can also check the, for the first model, you can easily tell that this AR1 coefficient is less than 1, so it is a valid AR1 model, and we do not have any like parameter redundancy problem because this is a AR1 model. Okay, so by checking the coefficient of significance, residual plots, what else? Let me see what else. Residual plots and AIC, BIC. The best model here is this ESA-RIMA 100 model. Okay. Okay, so that's the thing that we include the lead -3 in the regression model. Okay, and I also include lead -2 in the model. Okay, so for the lead -2, because we say that this lead -2 also has a very large correlation with sales. So I think it might be also be important to explain the sales. So the second thing I do is that I include the lead -2 in the regression model, but I only include lead -2. I do not include lead -3 at this point. Okay, and the first step is that we need to make the dimension of the data correct. And in order to do that, we throw away the first observations of the sales and the last observations of the lead. Okay, and I call this data DS2 and DL2. Okay. All right, and then I fit a regression model of DS2 and DL2, and I plot the residuals. So here's a residual plot. Not much difference from the residual plots by using lead -3. Okay, and let's check the ACF and the PACF. Okay, so it looks like that the ARIMA 100 might be a good starting point. Okay. All right, so that's the thing that I do here. So I first run this as ARIMA DS2 100, and the regressor I include is DL2, and here's what I got. Okay, so you can see that the coefficients are fine, not that bad. But for the residual plots, you can see that especially for this LB statistics, a lot of them are under 5% significance level. So that means the model is actually not a very good model. We perhaps want to change to some other models. Okay, and let's remember that the AIC and the BIC here is 2.84 and 2.92. Okay, so that means our starting point might not be a very good one. So let's go back to this ACF and the PACF plot and see what we want to include, what other orders we want to include. Okay, so clearly this PACF plot has a cutoff at leg number 1. So including AR1 is definitely good. And let's check this let's check this ACF. So this ACF, it looks like it cuts off, like if we do not interpret it in a tails off way, and let's interpret it in a cutoff way. So it looks like it cuts off at leg number 5. Okay, but leg number 5 is really large, right? So since we want to include less terms in our model, so how about we start with leg number 1? So that's the model I consider here. So it's an SRE model 101. So I only include one order of the MA in the model. Okay, and let's see what I got. So this is what I got. So definitely you can see that the things becomes better. So the LB statistics, all this LB statistics, the p-value are larger than 0.05. So this suggests that our model is a good model. And also you can check the ACF plot, the normal QQ plot, the standardized residuals are all good, okay? And moreover, we can see that the AIC and the BIC is smaller than the first model. So here is 2.77, but the AIC for the first model is 2.84. Okay, so definitely smaller. So that means this model as a RIMA 101 with regressor DL2 is better than the first model. Okay, but as I said, we realize that the ACF cutoff at leg number 5. So it might be possible that if we increase the order of the ACF a little bit, we can get some better model. So that's what I do here. So I do SRIMA DS2, but here I consider 102. Okay, and let's see what I got. Okay, so here's what I got. So you can easily notice that the LB statistics becomes much better than the LB statistics here, right? The p-value actually becomes very large, showing that it is very insignificant, showing that there's no reason or no much reason to reject our model, okay? And moreover, I checked the AIC and the BIC. It seems that the AIC and the BIC of this model is better than the AIC and the BIC of the previous model. So that's what I write down here. So AIC is 2.736 and the BIC is 2.858. Okay. Yeah, and actually I tried some other models as the RIMA 103, and I realized that there are a lot of like insignificant coefficients, and the AIC and the BIC becomes large. Okay, and I also try as a RIMA 104, and same thing happens. So the AIC and the BIC becomes large, and I do notice some insignificant coefficients. Okay, so again, by checking the coefficient significance, residual plots, AIC, BIC, the best model that we have here is this SRIMA 102 model, okay? But you can notice here, the AIC here is 2.73, while the AIC that we consider if we include lead minus 3, the AIC is only 2.366. So the AIC in this model is definitely better than AIC in this model. And the same thing happens for the BIC. Okay, so the BIC for the lead leg 3 model is better than the BIC for the lead leg 2 model. Okay, so that's what I write here. So, but it's worse than this model, this SRIMA DS3, sorry. This SRIMA DS3 100 DL3 model. Okay. Yes, it's definitely possible to have negative AIC and BIC. So AIC and BIC can be any values on the real line. This is very different from R square. R square can only be from 0 to 1. Okay. Yeah, good question. Okay, so that's what we have here. So it looks like the second part model is a model that we do not want. We do not want like lead minus 2. It seems like this lead minus 3 is currently the best model. Okay. And the final thing that I do here is that I try to include lead -2 and lead -3 simultaneously in the model, okay? But here, in order to do that, you need to be very careful with the data dimension, okay? So let's again use this very simple example to determine the dimension, okay? So the sales data, let's say, suppose it has 5 years, 2000 to 2004, okay? Because we have lead -3 in the model, we can only use 2003, 2004, right? Because if it is 2003, then lead -3 gonna be 2000. And if it is 2004, the lead -3 is 2001, okay? However, if you include sales 2002 model, there is basically no lead, there's no lead 1999 data for you to use. Okay, so that means you have like the wrong dimension of the data. Okay, and similarly, how about for lead -2? For lead -2, we can only use 2001 and 2002 data. Okay, right? So for sales 2003, it matches with 2001 lead -2. And for sales 2004, it should match with lead -2 2002 data. Okay, so having this in mind, let's find like what data we need to throw away. Okay, so for the sales data, again, we need to throw away the first 3 data points. And for the lead -3 data, we need to throw away lead -3. Let me see. Yeah, for the lead okay, so for the lead -3 data, we need to throw away the last 3 data points. Okay, and for lead -2, we need to throw away 2000, the first data point, and the last 2 data points. Okay, so we only use this middle 2 data points. Okay. Okay, and that's the code I have. So I think I might have some typo here. So this is a DS23. Okay, and this is gonna be DS232. Okay, so this is the lead -2. So we are throw away the first data points and the last 2 data points. Okay, and for the lead -3, we throw away the last 3 data points. Okay. All right. Yeah, so please very careful about like the dimensions here. It's not that easy. And I think like using some like very simple examples would help you to determine the correct dimension of each random variable. Okay, so now let me fit this model, fit 3 with DS23, DS232, and DS233. Okay, and I plot the residues. So here again, the residues looks like it's homoscedasticity, not that bad. It's no trend and no seasonality trend. And I run this ACF2 to find the ACF and the PACF of the SRM of the time series. Yeah, and looks like we have similar like ACF and PACF. So again, we think that using the ARMA, I think use the AR1 model is a good starting point. Okay, so here's what I use. So I use SRAMA DS23 100. So this is a starting point. But here is the difference part. Okay, so here is that we need to use this command, which is called like the cbind. So this is called like the column bind. Yeah, so it's that we put like DL232 in the first column and DL233 in the second column, and we combine them together. So this is like the column bind. Okay, and I call this data set DL. So if you have like more than one explanatory variable, you need to use like this cbind and put this binded data here. Okay, so if you use, let me write, if you use, just use, I don't know, DL232, DL233, I think it does not work. Yeah, it does not work. Or if you say like, if I put C something here, it does not work as well. So you need to combine the data first. Yeah, it says that you see like the length of the X and the X reg are different, do not match. So you need to like combine the data to bind the data first. Okay, so that's what I do here. So I run it. Oops, I think I didn't run this. Okay, so I run this model. And this is what I got. So this is the 100 model, which is the starting point. And I find, again, like all the coefficients are statistically significant. The intercept is a little bit insignificant. So let's keep this in mind. Okay. And yeah, okay. Yeah. But anyway, like the intercept is actually not that important, like in our analysis. So you can maybe just keep this in mind and see if we can find better models. Okay, and the residual plots. So the standardized residuals, ACF, normal QQ plots, are good, and LB statistics are also very good. Okay. Yeah, and the AIC here is, which I think I got it wrong. 220. Okay, so the AIC for this model is 2.117, and the BIC for this model is 2.220. Okay. And again, what I did is that I increased the order of the SRAMA model a little bit. And that's what I got. So I consider a 101 model. So it's ARMA 11 model. And I find like the coefficient of this MA1 is insignificant. Okay. And I find that the AIC and the BIC for this model is larger than the AIC and the BIC for the first model. Okay. Yeah, and further, I increase the order of the AR part a little bit. So I consider an AR200 model, and this is what I got. So again, I realized that the coefficient of this AR2 is statistically insignificant. And moreover, the AIC and the BIC again becomes large than the first model. Okay, so here I have something here. So by checking the coefficient of the coefficient of significance, residual plots, AIC, BIC, it seems that the best model is this SRAMA DS23100 and two explanatory variable, lead lag 2, lead lag 3. Okay, the AIC BIC here is 2.117 and 2.220, and it is actually better than the model that we consider in the first part. Okay, it's actually better than the model we consider in the first part. So the textbook only asks you basically to do this model, to do the part 1. So part C of the textbook basically asks you to do this part number 1. And you should conclude that this AR1 of the residue is a model that you want to use. However, I realized that if I include both lead -2 and lead -3 in the model, it seems that it is actually better than only including lead -3 in the model. And I realized that this model, so DS23100, so the order of the residual is 100, and the explanatory variable is lead -2 and lead -3. I realized that this model is actually better than the first model. Okay, so I think from here we can make some tentative conclusion. So that is, we find that, yeah, just as what I said, like this model is the best model. And actually we can do some interpretation here. So the interpretation is, yeah, let me write. So you can interpret the coefficients of DL232 and DL233 here. Okay. Yeah. Right. Okay. So let me see what else I want to talk. Yeah. Yeah. So this, I think that's pretty much all I want to talk. So that's the first 5 steps we use to fit a SRAMA model of Y with one regressor. Let's call it one regressor X. Okay. So that's what I discussed. Right. So next class, you can notice here that in all this analysis, there's basically no seasonality part here, right? All we fit here is the ARMA model, because you can easily tell that from this residual plot and the ACF and the PACF, there's no seasonality part here. But definitely this regression is very strong. It can include the seasonality part. I think which I will talk next class. I will give another example next class. I think like in your research project, maybe most of the data should have some seasonality pattern. Okay, for example, I see like the crime data. Some of you want to do the crime data. That data set has like a very, very strong seasonality, which is, I think, very interesting to lead 151 and lead 142. Okay, so in order to do the forecasting, but unfortunately, we do not have that data. So that means you cannot do the forecasting. Okay, yeah, but in some cases, you can do that. Okay, so for example, one example is that if you just use the time as your explanatory variable, then you can do the forecasting because you know that, say, like after year 2002, it's gonna be 2003, and it's gonna be 2004. So you know the information of the time after your full observation, which is fine. But for like this kind of explanatory variable, you do not know that. Yeah, but I realize that some of you want to study the effect of the cases of the COVID-19 on economy. So in this case, maybe you can arguing that, okay, maybe after some time, like after starting from, say, like May 2021, I expect the COVID-19 case would be 0. Okay, and then I just need to plug in 0 as like the future observation of COVID, then do forecasting. Yeah, but that's actually a very strong argument. Okay, you maybe need to do some modifications. So for example, let's say that I expect after May 2021, I expect the new COVID-19 cases every day or daily is, say, like under 30. Under 30 is not reasonable. Let's say under 1,000. And I assume like I just record 1,000 as, say, 0. I just do like some truncate data. So I assume like the COVID-19 case under 1,000, I just recorded as 0. Then you can do some forecasting, but you need to make like those arguments and say like why this is the case. Okay, so I will talk more about like the forecasting next class, and more importantly, like the code is not that simple. It's not like the simple as ARIMA 4. So I think I will spend some time to talk about next class, and in next class I will also talk about like this seasonality as ARIMA model fit for the residual. Okay, so any questions? Okay, so if there are no questions, I think that's it for today's class. Okay.
Thank you.